All right, folks, thanks for watching the test prep video. What is the sample space of the experiment? Here's what they want you to do. They want you to put a little curly bracket down, which is a way of saying, hey, I got a set of things. And you can see what can the spinner land on. It's 1 through 6, right? So 1, 2, 3, 4, 5, 6. What is the sample space? The event is landing on a prime number. 1, you can't count as a prime number, even though it's divisible by itself. And 1, which is kind of the definition of prime, for some reason, they don't include 1. So 2 is only divisible by itself and 1. 3 is divisible by itself and 1. No other factors. 4 is divisible by 2, so it's not prime. Right? So this is the answer for part A. Part B, we start seeing, well, 1's not a prime number, 2 is a prime number, 3 is a prime number, 4 is not a prime number, 5 is a prime number, 6 is not a prime number because it's divisible by 2 and 3. All even numbers, well, the exception of 2, are not prime numbers. Okay, so the sample space event landing on a prime number. I always like to read it again one more time, make sure I've listed the answers, haven't forgot any. Just take one more peek at it. That's what sample space is about. For an away game, baseball team can wear blue pants, blue or white shirts, and blue or white pants. And it says represents sample space 3 different ways. An organized list. Okay, so a list would have commas in between them. So like blue pants, blue shirts, right? Let's see here. I'm just wondering how I can say these are together. I guess I could put an ordered pair around them, and then I could say this is my list right here. Then I could say white pants with blue shirt, and then I could say blue pants with a white shirt, and then I would have white shirt or white pants with a white shirt. Okay, so that's one way to make a list. Table. Okay, so let's see here. I'm going to make my table out here. Might have a little bit more space. So this is going to be my shirts right up here. And this is going to be the pants over here. And then we go something like this. Blue, white, right? And so here we got blue, blue. We got blue, white. We got white, blue. And we've got white, white. Okay, there's my table. And then it says a tree diagram. So a tree diagram looks like this. You have a decision to make. Are you going to wear the blue pants or the white pants? Then you make another decision after you've chosen those blue pants. You say, I could wear my white shirt or my blue shirt. And then after I've chosen the white pants, I could say I could wear my white shirt or my blue shirt. Okay, so you can see there's 4 options here, 4 combinations. Here there are 4 combinations. Here there are 4 combinations of blue and white shirts. So that's what the idea of making a picture is helps you count the sample space. On a website showcasing outdoor patio plans, there are 4 types of stones, such and such and such here, 3 types of edging, 5 types of dining, sets, 6 grills, and all you have to do is take each number and multiply it together to figure out the total number of combinations. So 4 times 3 times 5 times 6, let's see, that's 12 times 5 would be 60 times 6, I think, is 360, unless I did some arithmetic wrong. So let's see here. Let A be the event the spinner lands on a 4 or 10. Okay, so you put in these parentheses here, you put 4, 10. That's our sample space. Let B be the event the spinner lands on a section with a number divisible by 4. Okay, so let's see. B is 4, 8, 12. I guess that's it. There is no 16. Let's see. And then A intersect B, we got to find the one that's in common. So 4 is the only number that's in common. That's what intersect means over there. That little symbol means what's in common between these 2 sets. Number 5. What's the chance of or what's the probability the card's a diamond and a seven? There's only one seven of diamonds. Here are the diamonds right here. Here's the seven right there, the seven of diamonds. There's only one of those guys, so it's 1 out of 52. A card selected from a standard deck of cards. What's the probability the card has a number on it that's divisible by 2 and is black? Okay, well, see, here are the black cards. Here are the black cards. That's a total of 26 cards. So my probability could start out like this. There's a total of 26 cards, right? And then how many are divisible by 2? What's the probability the card has a number that's divisible by 2? Well, there's 2 there, right? There's a 4, there's a 6, there's an 8, there's a 10, right? Now, let me think about that for just a second. If I go at it this way and I say, this is like saying, given I've got a black card that I already know is a black card. So if I put a 26 down here, maybe I haven't. Let's just, like I've said, there's lots of different ways to understand these probability problems. Let's go to total number of cards, 52, right? And if I count up the number of black 2s out of the total 52, we've got 2, 4, 6, 8, 10 cards out of 52, right? So there's 10 out of 52. That reduces it down to 5 out of 26. So 5 out of 26 is the right probability. I'm just saying, is there a way that we could have done that if we said, hey, we only have 26 cards that we're worried about. Those are the black cards over there. This probability, let me just read that again. What is the probability the card has a number on it that is divisible by 2 and is black? I don't think we can start with 26 in the denominator very easy. I'm going to think about that a little bit more. I think I should have started with 52 in the denominator and said, well, how many cards out of all these cards are both black and divisible by 2? And that is 10 total cards, because there's 2 right there, right? The 2s. The 4s are 2 more. And then the 6s are 2 more. There's two black 6s. There's 2 black 8s, and there's 2 black 10s. That makes a total of 10 cards out of 52. I'm going to stick with that answer. Sorry that I started you out with 26. There might be another way. I was thinking the other day there was another way of doing this. All right. Let's go to the next one. I think you probably could say there's 5 sets of black cards with. Anyways, we're not going to go there. Try to put total possible in the denominator every single time. Number 6. What's the probability the pig shows up and it gets right between these 2 pigs right here? Well, there's 6 out of a total of 12, because it's 6 plus 4 plus 2. I think the total is 12. And there's a distance of 6 that we'd be happy with a pig showing up. And so if it's random, it should be a 50% chance that if a pig shows up, it's going to get in between these 2 pigs right here. A certain store plays, this one, a movie on repeat, and there's a song in it that you really like, and you want to know what's the chance that you're going to show up during that song. So the movie is 2 hours long, 2 hours long. And the song only plays for 6 minutes and 31 seconds. So 6 minutes and 31 seconds. So what I've been telling people when I come over to talk to them about this problem is these 2 measurements have different units. So what I saw some people do is convert the hours to seconds. So if we did that, there's 60 minutes in an hour. So if we go let me put this in black so you know that the black one here is converting. So 2 hours. And if I multiply that by 60 minutes per hour, and maybe you've seen this in science where the hours are going to cancel out, they divide out. And now we're down to 120 minutes, right? And then I would have to multiply that by 60 seconds, right? 60 seconds in a minute. So the minutes would divide out. So we've got 2 times 60 times 60. Well, 60 times 60, that'd be 36 with 2 zeros. That's 3,600 times 2 is 7,200, right? So I've got 7,200 seconds that this movie plays for. And I want 6 minutes, 31 seconds of it. So 6 minutes. Okay, so let's do that again. Let's let's go 6 minutes times 30 or 60, 60 seconds in a minute. And so the minutes divide out, and we've got 360, right? But we've got to add 31 more. So this is 360 seconds, but when you add 31 more to it, you get 391 seconds. So now we've got, seconds and seconds, same units, and this is the probability that you show up. Now, is 391 and 7200, are they reducible? You could always go over to Desmos if you're not sure. And I saw somebody pretty, cleverly do something like, hey, what are the factors of 361? They just went to Desmos and to Google, and they said factors of 361. And where are the factors of 361 in prime factorization? I think they did this, and they said, okay, so we got 1 and 19. Let's see here. Oh, 19 and 19, or 19 times 19 is 361. Interesting. Oh, it's 391. I was going to say, this is not the number I remember. So 391. Let's do that one. So yeah, they got 17 times 23. And then they said, what are the factors of 7,200? So what are the factors of 7,200? And they were trying to figure out if, 17 and 23 were factors in there. And they're not, because the factors of 7,200 are 2s, 3s, and 5s. So anyways, you could just go 391 divided by 7,200, and you see this comes out, and then you hit the fraction. Oh, this is making me feel like they will reduce. No, it just put it as a fraction over here. That's silly. All right, so that's my answer. I've done the best I can to reduce it. Parachute is aiming to land in a circle that's 10-yard radius. Okay, and the field that they're definitely going to land on, so the total possible is a rectangle. That's 30 by 120. So I'm going to put 120 here. I'm going to put 30 there. 3 times 12 is 36. We got to add 2 zeros. So the total is 36 with 2 zeros. But then the circle is in here somewhere, and it has a 10-yard radius. So if I go pi times 10 squared, that's going to give me the area of the circle. And if we want a decimal, we'd have to go over here and go something like, let's get rid of this. And let's go pi times 10 squared. And then we're going to put that all over 3,600, right? 3,600. And here's our decimal, about 8.7%. So let's see here. This is about, let me make sure I have the right numbers over there. I do, I think. 8.7%. Notice I moved the decimal over 2 places, 1, 2, and the decimal ends up between the 8 and the 7. And if I want to round to the 10th place, let's say, I look over here to the right, and we're less than halfway to 8. So I'm going to leave it as a 7 right there. That's why I have 8.7%. If you want to put it as a decimal, then you're going to go 0.087. Now, we need to tell people that we rounded this. So I'm going to put a dot above these equal signs saying these are rounded answers. All right, Callie has a choice of 20 flavors. She gets 3 scoops. She wants the vanilla, chocolate, strawberry in any order on a triple scoop cone, right? So she's happy with a group of 3, one particular group of 3. So I'm going to put down 1 as her favorable, one group of 3. We want to know how many groups of 3 we can get. So if we ask 20, choose 3, it's going to tell us how many groups of 3 out of 20 flavors. So I just have to change this number right here to a 20, and I get 4,845. So I go 1 over 4,800, whatever it was, 4,845. 1 over 4,845. Now, this next one feels different, but I think it actually ends up being the same. It's kind of like you have 12 flavors of ice cream, and you want to know how can you get a group of 4 of them, and you only are going to be happy with one particular group of 4, meaning they're the 4 roller coasters, right? And that's what you're going to do first. Now, when it says like you're going to do that activity first. It feels like you could put them in order and do a permutation, but I think you can get away with doing a choose on this one, just like we did up here in the flavors of ice cream. You're happy with one group of 4, and you want to know out of 12 attractions, how many groups of 4 can you make? That's what choose is all about. It doesn't matter what order the people or the activities or the flavors of ice cream are in. You just want to know how many groups of 4 you can make out of them. So that's why I had a second ago, 12 over here. So that's 495. So I go 1 over 495, 1 over 495. So do you see how I'm using choose on my Desmos calculator here? We'll come back to that in class, and we'll talk about, could you have done this one as a permutation, if the order matters. But I don't think the order matters on that one. A die is rolled and a penny is flipped. What's the probability of rolling a 2 and landing on a tail? So what you want to do here is you want to figure out the probability of each one and multiply them together. Okay, this is a multiplication property. These are independent events. One does not affect the other. So what's the chance of rolling a 2 on a die? That's 1 out of 6. There's 6 options on a die. And then obviously there's 2 sides to the coin. So what's the chance we're going to land on one of those particular sides? That's a 1 out of 2. So we have a 1 out of 12 chance on number 11. Drawings taking place. One ticket from a set of 80 tickets, 1 through 80. If a ticket is drawn at random, what's probably that the number drawn is a multiple of 4 or a factor of 12? Well, let's see. Factor of 12. That doesn't, I don't think, introduce any new numbers. So like when I say, okay, 4 is a good one because it's a multiple of 4. And 8's a good one because it's a multiple of 8. Now, they're not factors of 12, but it doesn't matter because the word is or. If it was and, then we wouldn't include these numbers right here because they are not, they are factors of, what I'm saying is they're multiple of 4. They don't have, 8's not a factor of 12. So you don't exclude it because of the or word right there. So I don't think this adds anything, but I could be wrong. I'm going to think about it some more. Multiples of 4 are going to take care of also factors of 12. So anyways, I counted 20 over here when I list them all out. Now that might make sense because 80 divided by 4 is 20. So there should be 20, multiples of 4 over here. So I've got 20 out of 80 for my answer, which comes out to be 1 out of 4. Boy, I hope that makes sense. 15 cards, numbered 1 through 15, are placed in a hat. What's the probability the card has a multiple of 3 on it, given that the card picked is an odd number? So we said, there's a formula for this. And the formula looks something like this. The probability of B given A is happening, okay? And we said that is the probability of B intersect A. So the probability of B and A happening, and then all over the probability of A happening. But we said this formula is more complicated than you really need. Look, we can just, says probability of multiple of 3 on it, given the card picked is odd. Well, how many odd numbers are there? There's 1, 3, 5, right? We're just going to count them up. 7, 9, 11, 13, 15. I'm trying to keep my hand on the screen. That's a total of 8 cards. So my denominator, my total possible is 8 because we know the card coming out is an odd number. That's what it says, given odd number. Well, we're reducing this 15 number down to 8 possible numbers. And so what's the chance that has a multiple of 3 on it? Well, 3, a multiple of 3, 6, 9, notice I skipped over 7, right? 12 and 15. I think 5 of those odd numbers are multiples of 3. Okay, so 5 eighths. Now, we're going to have a conversation if you feel like I'm wrong on any of these problems. We're going to have that conversation in class. So that's part of our activity today. All right, how do you make a frequency table? You take the information and you put it into a table. So it says 15 males and 40 females drive SUVs. And then it says 35 males, and 10 females drive trucks. Then you add them up to get totals here. So this, I think, comes out to be 50. This comes out to be 50. This comes out to be 100. You add this way, you get 45. You get 55. Yes, the totals add up, right? Now, the thing I don't like when they give us 100 over here is when you write a relative frequency table, it's the same exact numbers. They're just percents over here. Like 15 out of 100 as a percent is 15%, because percent means per 100. I hate it when they put 100 over here because you can't tell like any difference between the relative frequency and just a basic frequency table, right? This is the two-way frequency table, and you can't tell this from this over here, the relative frequency table, because of the same numbers. Except, I mean, I guess you could put a percent sign, right? So we got 50% males, 50% females, 45% drive trucks, 55% drive SUVs. This has to be 100% over here, right? So this is really easy if 100 shows up as the total. Hey, I hope I've made this clear. Thanks for watching my videos.